All right, welcome back to section 2.2. There is, it's not your imagination. It's not my filming. It's there's a lot of construction noise outside, but I'm afraid I'd have to wait all day if, for that to stop. So I'm going to go ahead and continue, and hopefully my microphone and my filter are working. I'll talk a little louder than normal, and hopefully that works out. All right, so this is where we picked up, or left off. We're going to maybe overanalyze this. Now, I know some of you know how to graph this already, but let's take advantage of some of the things we just learned. So we're going to graph this by point plotting, but we're going to do a little trick where we're going to use symmetry to find some of our points. So that's the game that we're playing. And they find intercepts if you let x equals 0. Remember the equation was y equals x cubed. If you let x equals 0, you'll get y equals 0. And that's going to serve as both the x and the y intercept, because remember how you spot it. If x is 0, it's a y-intercept. If y is 0, it's an x-intercept. So that's going to be our only intercept. But the zeros are the giveaway. Next thing we're going to do, and I don't want to call it, so I don't want to say this is just for fun, but this is just to show the process. In y equals x cubed, replace y with minus y and ask yourself, do I get the same thing? And the answer is no. So it's not symmetric with respect to the x-axis. And what that means is when I graph this thing and get a point somewhere, I'm not going to get a bonus point down here on the other side of the x-axis. It's just as important to know that I'm not going to get these bonus points as it is to know I am going to get them. All right, let's try it again. Y equals minus x cubed. That's the test for symmetry with respect to the y-axis. And that does have a simplification, but the simplification doesn't lead back to my original. So another fail, another situation where if I have a point, I won't have a bonus point over here on the other side of the y-axis. And now, what if we replace both x and y with minus versions of themselves? I'll get minus y equals minus x cubed, and I could just multiply through by -1. I'll get y equals x cubed, which is exactly what I started with. And so voila, I have, if I have a point here, I'll have a bonus point on the other side of the origin. That's how we're using this idea of checking for symmetry. So they made the graph, the table, which I would normally just write this way. You pick your x values, calculate your y values, and notice what they're not doing. They're not putting negative values in for x. And the only reason why they're doing that is they're just picking positive values for x because we know something. We know a secret about symmetry. So as I go to, I think I mentioned I like to put these letters here so you can see where they're going. And notice that point D, 3,27, would actually be way up here somehow, because on this slide, 327 would be off the page. So really, I only have 3 points for this graph from my table anyhow. 0, 0, I'm calling A. 1, 1, which I called B, and 2, 8. Now, what they're saying here is symmetry with respect to the origin means that if you have this point, you're going to have this bonus point. It's I'm calling it B prime. I'm writing it this way. It's not a really important notation, just so you know what I'm writing here. But B, and B's kind of twin, or B's kind of bonus point. And then C, and the bonus point for C would be, instead of 2, 8, negative 2, negative 8. So by capturing a few points, I got more than the table offered me. And I should have an accurate graph, meaning the entire shape should have a shape on one side. The shape should be the same on the other side, not just the individual points. All right, new example. Now they're asking us to graph x equals y squared. This is unusual because to do this, this is a machine made to find x. So the right way to do this would be to pick y values, like pick y equals 0, y equals 1, y equals 2, and then calculate x is equal to 4, x is equal to 1, right? If I put in 3, why am I picking y values? Because y squared is the calculation that would give me, and it would immediately give me an x value. Now, I didn't pick negative numbers because I'm trying to play the same game they're playing here. And what they're saying is if you do the test for symmetry, you'll find out that it's symmetrical with respect to the x-axis. So let me go ahead and do this. I'm going to go ahead and put in y equals negative 3 on my table and just do this numerically. If y is negative 3, negative 3 times negative 3 is positive 9. So this is a point, but it's kind of a it's a bonus point that I really maybe didn't need to occupy in my table. Show you on the next slide. All right. So here's what the author did. Just gave us these values. Now, notice the author picked the y values. So y went first, and he calculated x values, and then when he brought this over here, the y values are after the comma. All right. But see this point. Well, let's see all these points. Here's the point I'm calling D, the point I'm calling C, the point I'm calling B, the point I'm calling A. Well, B has a reflected point in the x-axis. C has a point that reflects in the x-axis. And D has one because we tested it and it's symmetrical with respect to the x-axis. Remember the test for symmetry with respect to the x-axis. You replace y with minus y and you see if you get the same thing you started with. And we do, because minus y squared is the same as y squared. All right. Again, I don't know if that was really much of a win. In other words, if you were if your goal was just to draw this, and you just said here's A, B, C, D, and this is just a brand new point E, that would be fine. I think the author is just trying to introduce the concept and use the concept of symmetry. So when we're ready, we can use it for a more complicated image. And then the author just threw this in. It wasn't really a requirement, but they said, you know what? If you get rid of this part down here and just get rid of it, you've just created y equals the square root of x, which is a graph you should be familiar with. So y equals the square root of x and x equals y squared are very similar. It's just that x equals y squared keeps on going, and y equals the square root of x doesn't have this second part to it. Let's do it again. Another example, y equals 1 over x. You try to find intercepts and you'll find out it doesn't have any. Y equals 1 over, if you let x equals 0, that's undefined. If you let y equals 0, you'll cross multiply and you'll get 0x equals 1, which doesn't have any solutions. So no intercepts. Now, sometimes people think that's a bad thing, but it's a good thing to know exactly how many intercepts there are. So however I do this graph, I'm not going to cross or touch the x or y axes. Next step they're going to do is check for symmetry. And just go through these kind of quickly, but it fails symmetry with the x and the y-axis, but it does pass the test for the origin. And that is, if you put y and x, negatives on both y and x, you can simplify that to minus y equals minus 1 over x. Get rid of the minuses. It simplifies to what you started with before. So it is symmetric with respect to the origin. Now to graph this, keep in mind what we always do, right? If you solve for y, we're going to pick our x values. And they picked a bunch of x values here. The only ones that really mattered were these three here. So let's say you started here and you put in 2. Well, 1 over 2 would be, if x is 2, y would be 1/2, and give you this ordered pair. If x were 1, 1 over 1. If x were 1/2, that would be 1 divided by 1/2, which if you calculate that would give you a 2. So these are the points they put here. And again, the author's using the kind of built-in shortcut. If you know this is symmetric with respect to, either the x-axis, y-axis, or the origin, I didn't need to put in negative numbers in my table. The negative numbers will just come by symmetry. This is the point, the bonus point, A prime, B prime, C prime. And not only that, the entire figure is symmetric. So that shape should be the exact same shape on this side. This shape, by the way, is a shape we'll be familiar with soon, called a hyperbola. And the hyperbolas do look just like this. They do something else. They follow this line. It's this x-axis is an asymptote, so it gets closer and closer to that line. Not something that we're trying to learn right now at this moment, but it's a shape that you're going to need to know. All right, speaking of lines, what's the next section? Objectives. You've seen a lot of these before. Slope. Equation of a vertical line. Hopefully you're familiar with that. But anyway, we'll go over all of these one at a time. Even parallel perpendicular lines. So this is a fairly involved section. Okay, so our first one. The slope. So slope is the rise over the run. So if you have 2 points, you compare any 2 points. And it could be any 2 points. They don't have to be this close together. I could compare, I could compare, it's a much bigger rectangle, a much bigger triangle here. This rise over this run would be the same as, the rise over the run between any 2 points. So slope is rise over run. Now, that's just a way to remember it more than calculate it. We need something a little better than that to calculate it, and here it is. If you have 2 points, the change in y over the change in x, and let me actually write this so you can see it right on this page. Sometimes the change in y and the change in x are denoted by this triangle in front of those letters. The triangle is the Greek letter delta, change in y over change in x. All right. And be prepared to use that formula, I guess. You need it. So if you have a subtraction x2 minus x1, I guess what they're saying here is, hey, if the x's are the same, then the denominator would be 0. And if that's true, we call this the undefined slope. So this is a vertical line. Make sure you're familiar with that phrase, that word vertical line, when we get to it. So we can see that delta y over delta x, somehow it was off-centered here, so I wrote it again there. But all of these are the same idea of a slope. It's also sometimes called the average rate of change. We have some problems involving that later. Let's go on. You can read these bullet points, but let me get to a actual example. Read the bullet points if you like, but let's get to an actual example. All right, so here's an example. Find and interpret the slope. All right, find the slope m of the line containing these 2 points, 2, 8, 6, -3. All right, well, I have my x1, y1, my x2, y2, substitute those in, and we get a slope. What does this mean? It means that, well, the negative means the line's going to be decreasing. And notice they say for a 4-unit change in y, there's a change in, for 4-unit change in x, y will change by 11 units. Well, let's just say, so if I go 1, 2, 3, 4 this way, 4 points this way for x, I'll have to go down 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 for y. So this is what this line would look like. And the change in y, -11, over the change in x, 4, would fit this fraction if I were to write the fraction this way. Notice how they put the minus in the denominator when they calculated it a different way, and that would also be true. So we'll see those ideas later. All right, so I have this example. Next example. I didn't do the example. I just wrote a few things down, kind of what I was doing before. If they give you a slope, if you start somewhere, you know what happens. You know the rise is 3, 1, 2, 3, and the run, which you can think of as moving to the right, is 2. So if I go up 3 and to the right 2, I get that line, or that slope. Let's see, it looks like I started here on this one. If I start here and I kind of distribute the minus sign so it's somewhere, here is fine. My rise is -5, so I go down 5 and over 2. One thing I don't like about this example, when there's an example that has the same letter in it, same number in it, so students will ask me sometimes, is it always 2? Now, if this had been a 4, I would have gone 4, but I'm just interpreting the rise over the run, and we'll see this on a grid. So, example 1, it's really hard to see what they're saying here until I get to the picture, but this is a better illustration of what I had on that blank page. We're still doing that same problem, and that is if I have a point, a starting point, and I apply the slope, which is 3 over 2, I want to make sure that I rise 3 and I go to the right 2. Now, the way they did it, I guess it looks like there's an order to this. They went 1, 2 to the denominator, and then 1, 2, 3. I could have done that the other way, meaning, and I could have gone up 1, 2, 3 and over to the right 1, 2, and I still would have gotten that same point. Once you have 2 points locked in and you know it's a line, you can just connect them with a straight line and you have that point. By the way, in a regular class, I would not accept this. I always say graphs should fill the box. It's not a problem with an online class because the graphing software always fills the box, but there's something very important to us about how a graph leaves the box. And, we're not just interested in what happens inside the box, we're interested in what happens outside the box, and that's kind of important to us. This is the second part of that same example. You have a starting point, and you use the slope to find another point. So denominator is 2, the numerator we can think of as -5. It takes us to that point, and that gives us the graph. they're saying I could have looked at the point another way, but once you get one extra point, I think we're good. All right, well, this is pretty quick. You should recognize when you have when they say graph the equation of a line, x equals 2 might just be talking about the ordered pair on the number line, or the dot on the number line, not an ordered pair, but just the dot on the number line at 2. But in this case, they're saying no, we're talking about the line, and we want you to actually draw this on a grid. All right, and this is how you talk about x equals 2. X equals 2 is a vertical line. By the same reasoning, y equals a number like y equals -3 would be a horizontal line. So these are just things you should remember and be ready to answer if it comes up. Equation of a vertical line. All right, point slope form of an equation of a line. If you have any point on a line, y1, x1, y1, and you know the slope, this is what I call a good temporary equation of a line. The reason why it's temporary is it's not simplified. I haven't combined like terms. It's just kind of an awkward one to use, but and so we are going to work with it, but it is an equation of a line that we should know about. And it's useful in finding equations of lines. All right, so that's exactly what they're asking us to do. Find the point slope form of an equation of a line. What do they give us? They give us the slope and they give us the point. So I'm going to substitute for x, I'm going to substitute 1, this one right here. For y1, I'm going to substitute 0. And for the slope, I'm going to substitute a 3. So if you do all those substitutions, you actually get a simplified version of the equation, but they did a little bit of work, right? They removed this parenthesis here, and they did solve for y. Finding equations of lines from their description is a big part of Algebra 1 that you might remember doing. Then they went ahead and graphed it. All right, so that's the graph of that. New example, find the equation of a horizontal line. Well, this one's actually a lot easier than it looks. They went ahead and used that formula to find the equation of a horizontal line, but we kind of knew the equation of the horizontal line was going to be y equals blank. And if y is 3, in this example, it's 3 everywhere. So it would just be y equals 3. In other words, I think we would have known it was y equals 3 from what we're about to talk about. All right. When I say we're about to talk about, they tell us y equals b is the equation of a horizontal line. And if you know the y value once, it's going to be that y value for the entire horizontal line. This might be the equation that everybody thinks of when they think of the equation of a line. Y equals mx plus b. It's not unusual to take an equation in one form, standard form or the general form, and retool it to look like this. And one of the reasons we do that is when you write something in the form y equals mx plus b, it makes the slope visible. And visible is good in math. A lot of things in math are invisible. And if you want the slope to actually be something you can see and you can match up to the formula, put it in this form and the slope just appears between the equal sign and the x. So here's a multi-part example. We're given 2 points and we want to find the equation of the line. So step 1 is find the slope. So we find the slope using this formula, and it's just from the substitutions. -1/3 Once we have the slope, we're going to substitute, we're going to choose one of the points. It doesn't matter which one. They chose this one, 3, 2. It just substitute in here. So notice that if I hadn't gone and calculated the slope, I wouldn't have had the number to put in here. But I did have the x value, and I did have the y value. So what I'm doing over here is making those substitutions, that triple substitution there. Calculating, and when you solve for y, you put it in the format that we sometimes prefer, and that gives us the equation of the line. So notice where this started. All it had originally were 2 points. This point and this point. And by the way, I didn't do this to graph this. If I wanted to graph it, I already had 2 points. I could have just plotted those points and connected them with a straight line. We do this to find the equation. In other words, this is the answer to this problem. The answer to the problem is the equation. That's what we were looking for. Remember, it says find an equation of a line given 2 points. So y equals mx plus b is not the only game in town. A lot of students seem to be stuck on this, y equals mx plus b. The vast majority of questions start with the general form, or sometimes called the standard form, but the general form of a line, ax plus by equals c. There are a few things here. A, b, and c must be real numbers. It's even more than that. In terms of simplifying the general form, they shouldn't be fractions, but we'll get to where we will simplify it. But there's no reason for A, B, or C to be fractions. If they're fractions, we'll clear them. So there's a lot more to, a little bit more to this. So here is an equation in the general form. And they're asking us to graph it. And I think the process of graphing an equation in general form is a little faster than the book lets on. If x is 0, well, it's like this disappears, and I'm just solving 3y equals 6. So I know it's a 2. If y is 0, it's like this term disappears. And so I'm just solving 2x equals 6. I'm going to get 3. In other words, getting your points is really, really fast. This whole thing, making it look like a full step-by-step solution, just seems to be something we're carrying over from maybe Algebra 1. So keep in mind what I have here. I have my 2 intercepts. They're going to take a few pages to get there, but they'll catch up. If you let x equal 0, you find the y-intercept. And now, if you're ready to graph this, I can't forget which one I called A and which one I called B. Okay, as I remembered. All right. If I wanted to graph this, point A, point B, plot those, and you have your line. So I didn't have to solve, I didn't have to find the slope, I just had to find 2 points, the 2 points were the intercepts, and that's a good way to graph an equation. Let's pause this here, or start a new video. So I'm going to stop here and pick up again with a new video for parallel lines.